This video will demonstrate how simulating changes before physical implementation in a data center is necessary in order to understand all the effects. The example used is a common trend in data center management, switching air cooling unit blower fans with EC plug fans to save power. First, let's take a close-up look at the fans. Here you can see that in a blower fan the air enters through the side and is driven out downwards by the encased rotating blades. Here is an EC plug fan. For these fans, the air enters through the top and is driven out by the rotating blades in all directions. The EC stands for electronically commutated and refers to the way the motor operates the fan differently. It is 30% more efficient for the same airflow and also controls the fan flow to match the necessary cooling of the room. Because of the improved efficiency, many facilities swap to plug fans to save in energy costs, but are there other effects too? Let's find out. Here's one cooling unit with blower fans. We can see the general direction of airflow. Here is the simulation of the airflow pattern out of the unit into the floor void, coloured by velocity. On the other hand, here is a look inside the cooling unit with EC plug fans. The general direction of airflow is highlighted. The streamline results from the EC plug fan simulation show a different airflow pattern from the unit. When comparing side by side, it is obvious that the fans move the air in significantly different ways. The blower fans direct the air straight out from the cooling unit. On the other hand, the airflow from the plug fans is biased to the left in the direction the fans are blowing. There is also a dead zone that is not getting any air. Let's take a look at the fan comparison in a large data center room with 10 cooling units. On first inspection, it is obvious that the airflow from the plug fans is more angled, creating some vortices. Also, with the plug fans, there are some dead zones getting little to no air compared to the blower fans. These dead zones will cause cooling issues as the reduced airflow to cabinets leads to insufficiently cooled IT. Here, the three-dimensional net flow through each floor grill is plotted. There are some areas, like the one highlighted now, where the plug fans supply slightly more airflow through the grills. However, there are also some areas that get significantly less airflow, such as the following. This last area shows that the airflow through the grills from the plug fans is near zero for half the row. This is due to a no-flow area, as we saw earlier. Since Six Sigma Room catalogues the inlet and outlet temperatures of each piece of IT equipment, we can accurately determine what IT is overheating. Looking at the cabinets first, we have some overheating issues. If we take a look inside these cabinets, we can see which IT is overheating. This is a problem area for the original blower fans as well as the new plug fans. You can see that there are two blade chassis overheating in both cases. However, it can be seen that there is more overheating equipment with the plug fans than blower fans. While this is a hotspot for both cases, by switching to plug fans, the resulting change in airflow is enough to cause some IT to overheat that was only borderline temperature before. There are possible fixes for this problem, including changing damper settings on the grills, redistributing IT load, or installing underfloor baffling. But without simulation, it would be impossible to know the exact effect changing the fans would have on the room, and problems like the hotspot illustrated in this video would be unknown until physical implementation caused an IT overheat.